In this lesson, we're going to review our understanding of functions and functional notation from 1-2 methods. We're also going to be focusing on how this applies to the context of linear relations. Now, if we take a look at the graph that we've got here, you may have to think about what actually makes this graph a function. Now, we've got the graph of y equals x squared, so it's a parabola. We know that it's been restricted from -2, it's my x value, to +3. And the fact that this is an open circle tells us that it doesn't include -2. So right away, I'm hoping you can remember from 1-2 methods that the domain of this function is actually equal to an disclusive, or not including -2, to an inclusive 3. The range of this function is going to be the span of y values. That goes from the lowest value 0, and it does include that, to the highest y value 9. Now, I've called this a function a number of times, and there's a very simple test we can do, which we call the vertical line test. Now, no matter where I draw this vertical line, I know that I will only ever be crossing the function once. So we'll just clear that out so it's a bit easier to see. But what I'm saying is, if we draw a vertical line anywhere along the x values, we're only ever going to cross it once. Now, if it was to cross twice, then this wouldn't be a function. We may want to consider what this vertical line test actually means. The vertical line test is just a way of saying that when I sub a value in for x, I'm only going to get one y value out. That is, every time I sub in that value x, I will get the same y. So let's take, for example, a rule y equals 2x plus 1. Every time I sub in the value x equals 2, I'll only get one y value. So in that case, it'll be 5. Now you might think, when could this possibly not be the case? Suppose we had y equals 1 plus or minus the square root of x. Here, if I sub in the value x equals 4, then when x equals 4, y is 1 plus or minus 2. And so there are two answers. This is why when we get a graph you may remember from 1-2 as a circle graph would fail the vertical line test, because there would be two y values for the one unique x. Now, more than just talking about whether or not something is a function or a relation, so a function, remember, passes the vertical line test. A relation is still a rule we follow, but if we plugged in an x, we might get 2 or even 3 y values. Can't think of the time that you'd get 3, but I'm sure it's possible. Correspondence is referring as to whether or not this is 1-to-1 or many-to-1. Now, taking our quadratic function here, you may realize that if I sub in a positive or a negative answer, for the graph of y equals x squared, the y values are the same. Now, this doesn't mean that I subbed in an x and got multiple y's. It means that there are many x's which give the same y. And so we label this correspondence many-to-1. And a quadratic is a many-to-one function. In general, we can think of a function as a machine. If I input A, I get D, using my example here. So what I'm referring to is saying if I started at A, I got D. So we might think, oh, I've got the pair AD, or the coordinate AD. When I sub in B, I get C. So I've got another pair, B, C. C gives me B, and D gives me A. So I've got CB and DA. So the set of ordered pairs, in this case, is a 1-to-1 function. Now, looking differently here, we can see that in this case, A gives me D, but B also gives me D. And so if I thought about this in terms of ordered pairs, I've got AD, I've got BD, I've got C onto A, so C maps onto A, and D maps onto B. And so if I'm looking at this set of ordered pairs, there are 2 times that I get a Y value, but there is no repeat of X value. And what I mean by repeat of X value, I don't see that, I subbed in A and got D one time, and I subbed in A and got C another. So in this case, we would call it a many-to-one function. Before we move on, we might just state, if this wasn't a function, if this was a relation, I'd see another arrow coming out of one of these pairs. So I'd be seeing 2 arrows coming out of the input. So we mentioned from above that we want to state the domain and range of this function. And we already know what they are. We can see them here. But we might want to consider why. The domain refers to the span of X values. And so if I'm thinking -2, 4, this coordinate here, well, it means I've gone across to the left 2 and up 4. And this value 3, 9 means I've gone across 3 and up 9. So you can see that this span of X values is from -2 to 3. The open dot means that we don't include -2. That's what that open bracket means. The closed dot means that we do include the 3. Now the range is referring to the Y values. So my range of 0 to 9, although I've got an endpoint to 4, 4 is not the lowest point on the graph. The lowest point relevant to the y-axis here is going to be 0. And the highest point is 9. And I know that we've got a closed dot here, so this is both inclusive of 0 and inclusive of 9. So it's important that we're able to understand set notation and function notation. It's easy if we think, oh, the graph is y equals x squared, but how would we write that in functional notation? Well, we would start by giving it a function name. So this f with a colon means the function f, and the colon means is such that. So I'm giving it a letter, and then I'm saying these are the rules that that letter follows. The first thing that we'll find is a domain. So this is the domain over which the function exists. The next thing I'll see is an arrow, which means onto. Now, this means that when I say the function, the domain maps onto the real number field, that's what this R means, the real number field, that simply means that the output could be an irrational number. For instance, suppose that I subbed in the 4th root of 2. If y equals x to a quarter, that's the 4th root of 2, and we know that we're squaring it. Sorry, that's the 4th root of x, I should say, 2 to a quarter. We know that we're squaring it. That will give me 2 to the half, or root 2. Now, any time this function is a nice smooth line, like it is here, we're going to see this onto reals. In other words, when you see a function and it means onto reals, you can ignore it, because that will always be the case in math methods. Please do not think that this is the range. It's not. So again, when we're reading this sentence, the function f is such that its domain is -2, 3. Its output could be a real number. That's what it means onto reals. And the function rule is simply f of x is x squared. So suppose we wanted to calculate the value of y when x equals minus root 2. It's actually a little bit easier to notate in functional notation. If I said f of x was x squared, then f of negative root 2, that's just the thing that I'm subbing in. So I'm hoping that we can remember most of this from 1-2 methods. Let's see if we can put it into practice though. Which of the following sets of ordered pairs defines a function? So I've got two things here. I've got S and T. These are both ordered, a set of ordered pairs, I should say. So the squiggly brackets mean set, and the fact that we've got two open brackets and we've called them ordered pairs tells me that these could be coordinates on a graph. I know that this is not continuous, and I know that it is in fact discrete because it's just a set of 4 points over which this exists. Now I'm looking to see which one is a function. So looking at S, when I sub in negative 3, I get negative 4. So let's put that out. S, when I sub in negative 3, I get negative 4. When I sub in negative 1, I get an answer of negative 1. When I sub in negative 6, I get an answer of 7. And when I sub in positive 1, I get an answer of 5. This is in fact a 1-to-1 function. Now if I look at t is such that negative 4 maps onto 1, that's our first coordinate, and that coordinate is repeated. Well, that's good. I'm not going to redraw that. I'm then told negative 6 maps onto 7, but also that negative 6 maps onto 8. And this is my problem. I can't sub in an x value or an input value and get multiple y values. So which of the following sets of ordered pairs defines a function? S defines a function and T does not. So suppose we were asked to now put our functional understanding into a linear context. We're being asked to sketch the graph f over the domain negative 2 to 4. So there's my domain. And the graph is 2x minus 4. Well, 2x minus 4 tells me that I've got a y-intercept at negative 4. And I've got a gradient of 2. So that's going to be a straight line. Make sure that you guys use a ruler when you're sketching this. I know that I've got the point 0, negative 4. And if I want to find the x-coordinate, I need to let y equal 0 or let f of x equal 0. So 2 times the x-intercept minus 4 equals 0. 2 times the x-intercept equals 4, if I'm adding 4 to both sides. And the x-intercept must be 2. So I'll label that 2, 0. I'll need to label my graphs. This is going to be x and y, and this is going to be y equals f of x. Now the second step here is to take note of this domain. I only want the graph to function between negative 2, let's call this point here negative 2, so I don't want the rest of that, and I want 4. Now this is going to require that I redraw this graph. These endpoints I can see by the nature of the graph. I just need to sub in the x's to get the y's. They will represent my range because the graph is always going up. So I'm going to quickly redraw this with our appropriate points. So we know that we had 0, negative 4 and 2, 0. Because we have an inclusive negative 2, we should find f of negative 2, which is 2 times negative 2 minus 4, minus 4, take away another 4, which is negative 8. So my endpoint is negative 2, negative 8. Notice that I've used a closed dot because this was a square bracket. in order to find my endpoint, I know it occurs when x equals 4, but I don't know the y value. Well, that's as simple as finding f of 4. So that's 2 times 4 minus 4, which is 8 take away 4, which gives me a y value of 4. Now, what are the examiners looking for when we do this? Well, they're looking for consistency of notation. If I labelled y, I cannot call this y equals 2x minus 4 because the question asked me to sketch the function. So I'll need to label it y equals f of x. My endpoints and all critical points need to be accurate, and the shape also needs to be accurate. Now, a question like this would only be worth 1 mark. So you'll find there are many ways to lose the mark, and in fact many more ways to lose the mark than there are marks to be gained. So graphing is something we need to pay close attention to. So here we have g of x. We know that g of x is a quadratic, but it's only between -1 to 2. And in fact, this endpoint is not going to be included. It has to be an open dot. So let's start by finding the critical points. Hopefully we know that y equals x squared is just a parabola that looks like this. If I restrict it at -1, I'm going to have a value, and this one's going to be a bit higher because we're restricting it at 2. So g of -1 is equal to -1 squared, which is 1. So I have one endpoint at -1, 1. My other endpoint, g of 2, is 2 squared, which is 4. So we've got 2, 4. Sketching this graph, I know that I've got -1, 1, 2, 4, a turning point at 0, 0. I'll label this x and y and call my graph y equals g of x. There are a couple of things that we may want to consider when we're evaluating linear lines. That is that they can either be parallel, so their gradients are the same, but the vertical translation, or the y-intercept, is different. Or they could be perpendicular, which means that they intersect each other at a 90-degree angle. Another way to think about this is to say that the product of their gradients is -1. That is, the first gradient, let's call it m1, times the gradient of the second line, m2, is equal to -1. Now, if I solve this for one of the gradients, I'll find that one gradient is the negative reciprocal of the other. So I find it's easy to think to myself, flip and negate. If we want to find the gradient of the parallel line, we have to flip the gradient and then times it by -1. So, suppose we wanted to find the equation of a straight line which passes through 1, 2 and is parallel to this equation. Well, let's think about what we're asked to do. Now, the first thing we're asked to do, we'll put that in green, is that we're asked to find an equation. So right away, if you sketch a graph, you're going to be wrong. You need to make sure that your answer is an equation. Now, I know that it's an equation of a straight line. So I know I'm going to have y equals mx plus c. The context that I have is that this line passes through 1, 2, so that's a shared point, and is parallel to the line 2x minus y equals 4. So the first thing that I've thought about is, okay, well, I've got this point, x1, x2, sorry, I mean to say x1, y1, and I know that it's parallel to this equation. So if I could find the gradient of this equation, I will have found the gradient of my equation, the one that I'm looking for. So by rearranging just for y, you can see here, I get y equals 2x minus 4. So negative y equals 4 minus 2x, multiplying by -1, we get 2x minus 4, we just swap those around. And I know that my gradient is 2. Now this is the gradient I want. This is not the equation of the line. because you'll notice that if I subbed in the x value of 1, y equals 2 times 1 is 2, minus 4, that's not going to necessarily give me 1, 2. It's in fact going to give me 1, negative 2. So in order to find the line that I want, I'm going to use a formula. This is my formula here. Y minus y1 equals m outside of x minus x1. Now subbing in my gradient, which we said was 2, so that's me subbing in that gradient there, and my point 1, 2, when x is 1, y is 2, you'll find that we have an equation we can solve, that is y equals 2x. So this is the equation of the line that is both parallel to this equation and passes through that point. Now the only difference, if it was perpendicular to this equation, I'd still use this point, I'd still use this formula. But because this equation had a gradient of 2, my equation, if we flip and negate, is a gradient of negative a half. So imagine that 2 was 2 over 1. Well, flipping the fraction is 1 over 2, and negating is where I get that negative a half from. So, suppose we were asked to find the equation of the perpendicular bisector to 2x minus y equals 4 between the points negative 1, negative 6, and 2, 0. There's a lot to this question. Yes, we need to find an equation, but we also need to know what a perpendicular bisector means. Bisector, well, the word bi means two. Sector is referring to two sections, and in this case a perpendicular bisector means that we've got a straight line which hits the midpoint of these 2 points at a right angle. So not only is it perpendicular to this graph, but it's going to pass through the midpoint of negative 1, negative 6, and 2, 0. So let's first find the midpoint. That'll help me figure out what I know. So my x1, y1 is equal to the midpoint. Well, that's going to be negative 1 plus 2 divided by 2, and negative 6 plus 0 divided by 2. So the midpoint of the x and the midpoint of the y. So I end up with negative 1 plus 2, which is positive 1/2, negative 6 divided by 2, which is negative 3. So this is my point. My gradient, well, if I had 2x minus y equals 4, I might bring the y over and bring the 4 over, y equals 2x minus 4. My gradient for this line, m1, is 2. The fact that it's perpendicular means that the gradient that I want, let's call it m want, is equal to negative a half. Using my formula, y minus y1 equals m outside of x minus x1. I can substitute some things in here. I know that my point is 1/2, negative 3. So you see that that's actually a plus now. And my gradient is negative a half. So I end up with this odd thing that looks like y plus 3 is negative a half, x minus a half. And if I evaluate this, I'll bring the 3 over, so I'll minus 3 to both sides, and I'll multiply by negative a half. So I end up with y equals minus x on 2, that's me multiplying that one. Then I've got plus 1/4 minus, well, the number 3 could be thought of as 12 quarters. And so we end up with minus x on 2 minus, now we end up with 11 on 4. And that there is the equation of the line that I want. We can further this example by thinking if two lines 2x minus 5y equals negative 2 and 3x minus ky equals m are perpendicular and they intersect at negative 1, 0, find the values of k and m. Now lots of people try to instantly solve this through a system of equations, but there's 4 unknowns and only 2 equations, so it will never be solved with that. Instead, we have to think, what do we know about these 2 things that will allow us to solve just in terms of m and y? Well, I know that they intersect, so they both share the point -1, 0. That's like saying when x is -1, y is 0, or y is equal to 0. So let's sub that in. 2 times -1 minus 5 times 0 equals -2. Well, certainly -2 equals -2, but that doesn't help me. However, if I use it in my next equation, 3 times -1 minus k times 0 is equal to m. And so I find that -3 is equal to m. That's helped me already. So that's using one piece of information. The other piece of information is that they're perpendicular. Now, for this to be useful, I should solve for y. Using my first equation, might as well label them now. If 2x minus 5y equals -2, minus 5y equals -2 minus 2x, and y equals 2x over 5 plus 2 over 5. Solving for the opposite here, 3x minus ky equals, remember this is -3 because that was my value for m, bringing the 3 over. Negative ky is -3x minus 3. And if I divide by -k, then y equals 3x on k minus 3 on k, which it's a plus now. So I know that these are perpendicular. So my gradient 3 over k is perpendicular, so we'll draw 2 lines at a right angle, to 2/5. That means that 3 over k must be equal to the negative reciprocal of 2/5, or -5 over 2. Now if I want to solve for k, I can bring the k forward and multiply by 2. So I get -5k equals 6, and k equals -6 on 5. That's the second part of my answer. So it's important here that we use the context we're given. If we're not spending time reading and breaking down the question, you're not going to do well. One of the things you can do is think, what is the question asking me to do? So that's in green. What am I asked to do? What are the 2 things that I have, or the many things that I have? In this case, we had one equation and the other. And then what do I know about that stuff? What is the context? Now there's a couple of extra things here which I'm going to let you work through. So how do we find a midpoint of a line? And that's always just going to be a formula. I'm sure you could go through that, but it's best to have it inside your notebooks just in case. The distance between 2 points is just an extension of Pythagorean theorem, but again, it's just a formula. So it's something that I'm sure you could put into your reference book and practice, practice, practice. For example 3, we're going to quickly do this just so you've got a record of it. Calculate the midpoint and exact distance between the following 2 points. Well, let's start with midpoint. In fact, let's actually start with labeling what we know. This is going to be my x1, y1, so that's my first point A, and this will be my x2, y2. I know that my midpoint, so my midpoint, is x1 plus x2 on 2 and y1 plus y2 on 2. It's just going to be a coordinate. It's half of the corresponding x's and half the corresponding y's, or the average is one way to think of this. So x1 plus x2 on 2, actually I don't need a bracket just there, and y1 plus y2 on 2, well if we're subbing that in, negative 1 plus 3 is 2. 2 plus negative 4 is negative 2. And we can see here that our midpoint is just going to be 1, negative 1. So if we evaluate that in purple, 1, negative 1. There's no need for me to give units or contextualize my answer because a midpoint is a midpoint. However, for the distance, we might think our distance s is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Now in class we'll do the proof for why this is, but it's just Pythag theorem. If I sub in what we have, something squared plus something squared, well, x2 was 3 minus negative 1 is positive 4. And y2 was negative 4 minus 2 is negative 6. And so we end up with the square root of 16 plus 36. So we can evaluate this. 4 squared is 16, negative 6 squared is 36. And so we're left with the square root of 52. Now if I want to simplify that surd, I could think, 52 is a product of 4 and 13. So square rooting both of those will give me 2 root 13. So the answer here is 2 root 13, but remember we're after distance, so we'll put in units. I don't know that these are measures of centimeters or meters, but I do know that they're linear units. It's a distance between 2 points. Here's a further example that you can use to check your understanding. For example 5, we'll make it slightly harder. It says find the value or values of x so that the distance between these 2 points is 13 units. Well, what have I got here? I've got 2 points. I need to find the value of x. Find the value of x. Well, it's a good thing that x is one of those points. And the context here is that the distance is 13 units. Well, I know that my distance formula, x2 minus x1 squared plus y2 minus y1 squared is equal to 13 units. I do have an x1, y1, and I do have an x2, y2. So subbing this into our formula, the square root of x2 minus x1, so that's 6 minus x squared, plus 19 minus 7, so that's going to be 12 squared, is equal to 13. So the square root of 6 minus x squared plus 144 is equal to 13. If I square both sides, we get 6 minus x squared plus 144 minus 169, so I'm just minusing 13 squared, is equal to 0. So if we're looking at this now, 6 minus x squared, now the difference between 144 and 169 is going to be 15, so minus 15 equals 0. 6 minus x squared equals positive 15. 6 minus x is equal to plus or minus the square root of 15 because x could be a negative number. And if I bring the 6 over, we'll find negative x is negative 6 plus or minus root 15, and x is equal to 6 plus or minus root 15. And so I have two answers here for x, 6 plus root 15 and 6 minus root 15. Now the final thing we want to think about here, and it doesn't always come up, but when it does, people usually forget. It's important to note that if the tan theta, so the tangent of theta, is equal to the opposite side over the adjacent side, then it's true to say that theta, or tan theta rather, is equal to y2 minus y1 divided by x2 minus x1. Now this is because to get to this point, I've gone all the way up to y2, and I want to subtract this point, which happens to be y1. Now you might think, okay, if I said to you that tan theta is y2 minus y1 over x2 minus x1, that's the gradient. And it turns out that tan theta is equal to m. So if I want to find the gradient that a straight line makes with the x-axis, all I need to do is do tan theta. If I want to find that the angle, or what angle it makes with the x-axis, I'd have to find its gradient and then do the arctan, or the inverse tan of that gradient. So determine the gradient of a line passing through 3, 2 and 5, 7, and the angle theta that it makes with the positive direction of the x-axis. Well, I found here that my gradient is 5 over 2. I think we can all do that. And if I use the fact that m equals tan theta, then I'd say, well, tan theta is 5 over 2, and the inverse tan of 5 over 2 is 68.2 degrees. Now this is a little bit odd when it's a negative gradient though. And in general, all we'd need to think is find that internal line and then do 180 minus that angle. So using the similar question here, I found the gradient is negative 4 over 3. So if I did m equals tan theta, and I got negative 4 over 3, then the arctan of negative 4 over 3 is 53 degrees. Now let's think about this. That means that my inside angle is 53 degrees. So the direction, if I'm thinking about the outside angle, which I might need to consider, that's going to be 180 minus 53 degrees. So just keep that in mind. Is it asking for the direction with the positive x-axis? In this case, it was with the positive. And so I've got to be thinking from the right side, from the positive side. And so the angle that we're after is actually going to be 180 minus 53. And that gives us the 126.87. Let's put this into practice. Find the angle, correct to 2 decimal places, that the line joining the points 3BA, 3AB make with the positive direction of the x-axis. So I've got to find an angle, and I've got 2 points. Let's start by finding the gradient. M is equal to B minus A divided by 3A minus 3B. Now if I take a negative out of the top, then I've got A minus B, that's one way to take out a negative, divided by 3 lots of A minus B. And so we can see here, I just took out a common factor of 3, that the gradient, although I didn't get any points, my gradient is actually equal to negative 1/3. So if tan theta is negative 1/3, then theta is the arctan of negative 1/3. Now notice that this is a negative gradient. So whatever answer I get here, I'm going to then need to do 180 minus that answer. On my calculator, I find that theta is equal to 18.43. Now, I actually get negative 18.43, but because we're treating this as just find it and then do 180 minus, I can just make that positive. So I'll pretend that it's positive 18.43 and say that the actual angle that I want is 180 minus 18.43. So 180 minus 18.43 gives me 161.57 degrees. And that's the angle it makes with the positive direction of the x-axis. So what can we hopefully learn from this very long lesson? Well, can you read and write in functional notation? Can you find a domain? Can you apply the property n equals tan theta? Can you find the distance and midpoint of 2 points? Some other things that we did was we also found the equation of a line. And some basic sketching linear graphs is also helpful.